All right, so in the last lecture, we talked about this idea of Fermi estimation, trying to combine things we know about the world with a particular technique for breaking down problems to try to come up with quantitative estimates of all kinds of things in the world around us. Right? And so we talked about this systematic method for approaching these problems. Step one was to kind of look at the original problem and try to break it down into smaller subproblems that maybe are easier to individually work with. In step two, we came up with numerical estimates for the relative sizes of all of those subproblems that we broke things down into. And we introduced this geometric averaging technique in the event that we still had really just a poor guess of about how big some number was. And we said, taking the geometric mean somehow includes both information from our underestimate and our overestimate of a problem in a way that taking a normal average neglects, right? So this is a very powerful technique for these order of magnitude problems. Right? Once we came up with all of those different estimates, you can then just combine everything into an order of magnitude estimate of your answer to the whole problem. Right? And then, of course, steps 4 and 5 are to really sit back and think about the answer you came up with, interpret it, and refine any of the approximations you made as needed. Right? So I kind of want to walk through a little bit more involved of an example. The thing we used to kind of illustrate this originally was a crowd estimation problem. We put up an image of an aerial shot of a crowd, and we said how many people are there. And let's use the same set of steps and techniques, but work through a slightly more involved question. So the case study that I want to do here, which we've called the trees and paper, is to answer the following question. Right. So question I have like an environmental concern, and I want to know how many trees are used to produce toilet paper in the US every year. US every year. Great question. Well, it's a question anyway. And this is one of those things where it's like, where do we even begin, right? Like at first glance, you might be tempted just to give up or just to guess wildly, Is it 10,000 trees per year? Is it 1 billion trees per year? It's probably not either of those two extremes, but I don't really have a great sense of where to start. I know essentially nothing about trees, the industrial production of toilet paper, or the toilet paper habits of anybody other than myself. And I don't want to know, right? So fortunately, this kind of systematic method that we outline gives us a roadmap for how we can start breaking down this problem. So let's follow those steps and see what kind of number we end up with. Right. So step one is problem assumptions and problem breakdown, right? And the first thing that we might want to say is, okay, this is a question about production of toilet paper in the US every year. Let me make things simpler by assuming that that's the same as toilet paper consumption, So assumption one is just production equals consumption. That doesn't have to be true. The US might be a big exporter of toilet paper. It might be a big importer of toilet paper. I have no idea. And so to make an order of magnitude guess, let's assume that it's producing about as much as it consumes. Right? So if I make that assumption, then I want to break down my problem into several pieces. I want to say, okay, how many people are there in the US? So number of people in the US. And then maybe I say, if I break this problem down of toilet paper consumption into how many people are there in the US, and then, toilet paper use per person, per person. And then, step or item C might be, how much tree does it take to make toilet paper in the first place, right? So I've taken this big problem, how many trees do we need every year, and kind of broken it down into a set of things that are individually easier for me to estimate, right? And so hopefully because those are easier for me to estimate, I'll end up with a better overall approximation for my system. Okay, so step 2 was to try to come up with independent estimates of the size of all of the factors that we just broke things down into, right? So item A above, how many people are there in the US? That's kind of an easy citizenship question, being being aware of the place you live is important, and I know that there's about 330 million people in the US. That's great. I actually am not sure if that's only US citizens or if it's citizens plus non-citizen residents. Doesn't matter. We're all using toilet paper more or less the same way. So there we go. 330 million. That's a great sense of scale. Now, how much toilet paper do people use per year, per person? I don't really know. I don't know how much each person uses per year. As I said, I don't really want to know how much other people use. If we combine, all of the varied uses of toilet paper, you might make an estimate, well, it can't be that different per person from about, 1 or 2 rolls per week. Maybe it's a little bit less, maybe it's a little bit more. You can keep any information you have to yourself. I'm going to say, 1 to 2 rolls per week. And I'm going to split the difference there and say, let's call this about 70 rolls per year. Rolls per year per person. And I've kind of started with the things that I have the best sense of how to estimate, right? But now we get into part C. How do I think about how much tree it takes to produce a roll of toilet paper? Tree per toilet paper. Great question. But let's break this problem down again into a set of easier things that we can try to estimate. So let me switch colors here and make a handful of guesses. First you might say, how much does 1 roll of toilet paper weigh? And units are just a convention of convenience. And for me, because that's what I grew up with, it's actually still easier to think in imperial units sometimes. So I'm going to say that the answer to this is, more or less half a pound per roll. Just as a rough guess, right? So now I have a way of saying if I can figure out how much a typical tree weighs, and I make some guesses about turning wood into paper, I have some conversion factor I can use to turn that into rolls of toilet paper. Okay, that's great. So now we're confronted with this question of how much does a tree weigh? And I don't really know. How much does a tree weigh? Again, great question. How might we go about starting to estimate this? I'm going to break this part of the problem down even further, right, into a measure of how much volume a tree has and an estimate of how dense a tree is, right? Because those are things that are maybe a little bit easier for me to imagine. Okay, so what is a normal tree shaped like? It's shaped like a tree. I'm going to imagine that we're thinking about a pine tree or something like this. And you can see that there's a reason I became a physics professor and not an artist. So I want to estimate, how much volume is in a typical tree. And the real tree shape here is super complicated. I'm going to replace that because, again, this is like an order of magnitude estimate. I'm going to pretend that this tree is just a cylinder. Right? And so I'll say, I don't know, maybe this pine tree, a typical pine tree is maybe 40 feet tall. 40 feet tall. Maybe this diameter is 2 feet or something like that. Real trees are complicated. This is just an order of magnitude estimate of, some typical representative tree. And then if I do just a little bit of geometry, and I say, what's the volume of this type of cylinder? Well, the area of this circle is pi times the radius squared. I picked 2 feet because the radius is 1, so that makes it kind of easy. So let me say pi times 1 foot squared times 40 feet. In height, so base times height, and that's telling me that my tree is about 125 cubic feet in volume. Okay, so we've just said how much does a tree weigh, and now, what's the density of a tree? Of tree wood? Again, great question. I don't know, what I do have a sense of, using this kind of geometric averaging technique. Okay, so I grew up in a house that we needed to heat with firewood, so I've carried small logs around. And if I think about a cubic foot of tree, I think, well, it's definitely more than 10 pounds. And it's definitely less than 100 pounds because I could carry it, but it wasn't that easy to carry, right? So my underestimate is 10 pounds per foot cubed, and my overestimate is 100 pounds per foot cubed. I know it needs to be somewhere in this range, right? And so the trick that we talked about says, oh, well, then the estimate I should use should be like the square root of 10 times 100. And I'm just going to approximate that, dropping some of the extra significant figures, by something like 30 pounds per cubic foot. Okay, just as a rough guess. Okay, so, I now have an estimate. If I combine these two items, how much does a tree weigh with how dense is tree wood, I have an estimate of how much volume a tree has with how much density the tree has. So I have a combined estimate of how much a typical tree weighs. I have an estimate of how much a roll of toilet paper weighs. And so that means, the last thing I need is an estimate of, converting wood to paper, some particular type of paper in this case. And again, I don't know anything about industrial production mechanisms, and I'm going to just kind of use common sense here. I think getting like 99% yield, like I have exactly as much paper at the end of a process as I had wood that went into the process, that feels unreasonably effective, right? There's always some amount of loss. I think if you only had a 10% yield, that would be a really bad industrial process. And maybe for some complicated things, that's what you get. But like we've been making trees for a long time. And so again, I'm going to say, my underestimate is that, 10% efficiency would be bad. And my overestimate is that 100% efficiency or 99% efficiency is, unreasonably good. So again, I'm just going to guess that about 30% of whatever wood you start with, 30% of, let's say, wood by mass, gets converted to toilet paper. Okay, so there you go. I've kind of broken down this problem repeatedly in as many steps as I needed. We started out by saying, what's the total consumption of toilet paper in the US? We broke that down into, well, how many people are there? How much do people use per year? And then, we said, well, now we need to know how much tree it takes to make toilet paper. And we broke that down itself into a sequence of steps that were maybe a little bit easier for us to apply our common sense reasoning and make some kind of rough numerical estimates of. Okay. So we've got all of the numbers that we need. So we're ready for step 3. Step 3, which was just combine everything. Combine everything with some enthusiasm. So let's do that. We started out and we said that there's about 3.3 times 10 to the 8 people in the United States. We said, they're using more or less 70 rolls of toilet paper per year for 1 year. 1 person year, if you like. We said there's about half of a pound for every roll of toilet paper. So we're going to do this, extended units conversion. We're multiplying that by, we said there's 1 tree that goes into 125 cubic feet. We said a cubic foot, so 1 foot cubed, was about 30 pounds. And scrolling over a little bit because I'm running out of room, we said that there was about, let's say, 100 pounds of tree per 30 pounds of paper, right? And if you're doing these units carefully, you would distinguish, this is half a pound of paper, this is pounds of tree, this year is really person years or people years to make the units actually work out. But there you go. We have this extended sequence of factors that we can all combine together. And if you do the multiplication, that works out to about 1 times 10 to the 7 trees per year. Okay, step 4. Interpret your answer. Actually, that seems like a lot of trees to me. 10 million trees per year. This is honestly a bigger number than I was expecting to get when I started this process. On the other hand, I kind of know that the US, all told, probably has on the order of hundreds of billions of trees, if you count, every tree in the entire country. So I like the fact that 10 million is less than 1% of all of the trees in the US every year. So at least in that sense, this order of magnitude estimate, doesn't feel like it's radically too big. If I had gotten a guess that said the US uses 10% of all the trees that it has every year to make toilet paper, I would say that kind of defies my intuition for what the order of magnitude of this answer has to be, and I must have made an error in my assumptions somewhere. Okay. So my number feels like it's pretty big, but it's not like unreasonably humongous, so that makes me feel good. Actually, the other thing that I'll tell you is that I picked this particular case study because when I tried to look up the answer to this question on the internet, I found numbers that were just all over the place. And so it's actually hard for me to know what the right answer to this question is. All we have to go on are this type of reasoning, which if we want, we can refine as much as possible, right? And so just to give you a few examples of, how my estimates compare to other people's estimates, I found some estimates that one tree can be converted into anything between 200 and 2,000 rolls of toilet paper. This was mostly from industry websites. And, this is itself a pretty big range for a typical tree. And if you look at our estimate here, a tree is about 125 cubic feet, which is a certain number of pounds, which has a certain efficiency, and which you're aiming for a typical kind of target weight. Our estimate is on the high end of this. Our estimate was one tree goes to about 2250 rolls. Okay, so we're like on the high end of some estimates, but we're not unreasonably high. On the other hand, I tried to look up some answers just to the whole problem. And, one article that I found in National Geographic estimated that we use 27,000 trees per day on toilet paper worldwide. Okay, so this is in a different kind of set of units than what we estimated in, but we can convert it pretty easily, right? So 27,000 trees per day, multiply that by how many days there are in a year, and you end up with an estimate of about 10 million trees per year. That's the same, number of trees, but this estimate was for the entire world, and our estimate was just for the US, right? So that's suggesting that our estimate is too high because, we would have had to multiply not by the population of the US, but, a number which is an order of magnitude bigger, On the other hand, I found yet another article, this one in Scientific American, that estimated that the US uses 15 million trees per year on toilet paper production. And, this is a number that's right in the same ballpark as the estimate that we made. I point out in the lecture notes, I found yet another estimate that said the range could be anywhere from 40 million trees to 1.8 billion trees per year. And I don't trust that website because these two numbers are so different from each other that they can't come from the same kind of way of estimating things, right? So, this was an interesting exercise in saying I actually don't know what the answer to this problem is, but I can think about the order of magnitude number I got in several different contexts. I can look up estimates for particular pieces of my breakdown. I can look at different estimates for the final answer that I got and kind of reason about, well, what do I think is the appropriate kind of order of magnitude scale here? Okay. And then finally, step five, refine your results, is something that we could definitely do. I don't necessarily want to spend a lot more of my time guessing trees used to make toilet paper at the moment, but we could definitely go back and revisit every single assumption that I made. We could, if you want, look up or try to think even harder about, this number. What really is the efficiency of converting an amount of wood to an amount of paper? Maybe I could get a better estimate of the density of tree wood. Although actually I think this is probably right in the correct ballpark, whereas this is a number that I have a much worse sense of. I made this kind of combined estimate of how much does a tree weigh, right? By combining volume and density. What type of trees, though, are even used in the production of toilet paper? Is it hardwood? Is it softwood? What year are trees typically harvested at? This kind of estimate of a 40-foot pine tree, which is 2 feet in diameter, that on its own could probably be off by more than a factor of 2, depending on the details of, what typical trees are actually used in some process, rather than kind of a stereotypical tree in my imagination, right? And I could also think a lot harder if I wanted, at least about part 2, or step B, I should say, of this, how much toilet paper is actually consumed. I know my estimate of the population is good, but the kind of combined estimate here could be refined, right? Some fraction of 33 million are babies and young children, and they probably use a different amount of toilet paper than adults and the elderly. And, I could think about both the amount of toilet paper you use, not only in terms of how much you buy, at the grocery store, but also, home use plus office use plus public use and all of this stuff. So I don't actually want to, but you could certainly go through this and, make better assumptions, make better approximations by thinking harder about any of the, sub-problems we broke things down into. And again, the goal is not to get precisely the right answer, but rather to really start understanding what it's like to, just feel our way around orders of magnitude, attaching numbers to the things we see, and the kind of quantities that determine, not only how the physical world works, but how the social world works and how our constructed society works. Okay, so I make a comment in the lecture notes that one of the other nice things about this style of problem is that it's really easy to just make up as many examples of things to try to estimate as you might want. None of us is an expert in anything. Certainly not an expert in everything. Maybe we're an expert in something ambiguous. But so you can just kind of, make up huge numbers of things that you could try to estimate. So in the notes, I have a bunch of examples. How many total hairs are there on all of the heads in everybody in the city of Atlanta? What is the total length of grass that grows on a typical, well-watered suburban lawn in the summer? And how much water do you waste trying to get that grass to grow? You could try to estimate how many people are looking at Facebook at this very instant. You could ask how many M&Ms are in a jar at a fair where you're trying to guess the number of M&Ms so that you win all of them and get to eat them, right? So one of the homework problems, which will be posted later on, will be to kind of work through an example of these Fermi problems. And it's not about getting exactly the right answer. And it's definitely not about looking up the right answer. It's about, saying, how can I sit down and just try to think my way through this problem, systematically break it down, come up with reasonable guesses, and then, see where we end up.